Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module, we are discussing volumetric analysis. The contents of this module are quantitative analysis, introduction to volumetric analysis, standard solutions, primary standard, secondary standard, end point and equivalence point, introduction to indicators, and different type of titrations as an overview. First of all, we are discussing about quantitative analysis. In analytical chemistry, there are two types of analysis. First one is qualitative analysis and second one is quantitative analysis. In qualitative analysis, we are finding out the type of components present in a given sample. However, in quantitative analysis, we are estimating the amount of the substance present in a given sample. So, qualitative analysis and quantitative analysis are two important analytical stages or analytical procedures in analytical chemistry. In quantitative analysis in chemistry refers to determining the amount of or concentration of substance in a sample. The quantitative analysis involves precise measurements and is essential in various fields including pharmaceuticals, environmental testing and industrial process. Inorganic quantitative analysis. Inorganic quantitative analysis involves the estimation of ions or radicals or components present in a given sample. There are different kind of inorganic quantitative analysis. The three major types of inorganic quantitative analysis are volumetric analysis, gravimetric analysis and analysis with the help of instruments or instrumental analysis or instrumental methods. Now, we are entering into volumetric analysis. That is, we are now having an introduction on volumetric analysis. That is, our title is Introduction to Volumetric Analysis. Volumetric analysis is a quantitative analytical method used to determine the concentration of an unknown solution by reacting it with a solution of known concentration. So, in volumetric analysis, there are two kinds of solutions. One solution with known concentration and other solution with unknown concentration. So, in volumetric analysis, we are determining the concentration of an unknown solution with the help of other solution with exactly known concentration. So, volumetric analysis involves measurement of volume also. Here we are finding out concentration of an unknown substance with the aid of the knowledge of concentration of another substance. Volumetric analysis involves measuring the volume of the reagent known as titrant required to complete the reaction with the analyte. The analyte means the substance being analyzed. So, in volumetric analysis, there are two types of substance as I just mentioned. They are the titrant and the analyte. Analyte is the material whose concentration is to be determined. And the titrant is the material with known concentration, with exactly known concentration. Now, we are having a discussion on the principle and procedure behind volumetric analysis. That is, we are discussing volumetric analysis, principle and procedure. Number of milli-equivalents of the analyte solution is same as that of the titrant. How is it possible to find out milli-equivalent of an analyte? Milli-equivalent can be easily connected to normality. Normality multiplied with the volume in ml gives you the value of milli-equivalents. In volumetric analysis, there are two types of materials, one titrant and one analyte. And the basic principle behind the volumetric analysis is that number of milli-equivalents of the titrant should be same as number of milli-equivalents of the analyte. That you can represent like this: N1 V1 equal to N2 V2, where 1 stands for either analyte or the titrant. N2 and V2 stands for the normality and volume of the second component. So, we can specify this point more clearly. Number of milli-equivalents of the analyte should be equal to number of milli-equivalents of the titrant. N1 V1 equal to N2 V2. N1 V1 that represents normality into volume of the first component. That means milli-equivalent of the first component. N2 V2 means normality into volume of the second component. That is milli-equivalent of the second component. These two milli-equivalents of the first component should be same as milli-equivalents of the second component. And in this expression, N1 represents the normality of the solution. Let 1 be analyte. Then V1 represents volume of the solution, that is solution 1, that is analyte. So here 1 stands for analyte. At the same time, N2 and V2 represents the corresponding quantities, that is normality as well as volume of the titrant. So you can say that it is very well clear that number of milli-equivalents of the analyte N1 V1 should be same as number of milli-equivalents of the titrant, that is N2 V2. Now, we are continuing the procedure of the volumetric analysis. In doing the volumetric analysis or the analytical procedure, a known volume of the solution of unknown concentration, that is the analyte, is taken using a pipette into a conical flask. Now, a solution of known concentration, that is titrant, is added from the burette until the reaction is complete. This setup is shown diagrammatically here. Here you can see a conical flask. The conical flask contains analyte solution, and above which you can see a burette. Burette is a glass rod. Generally, it can be loaded with 50 ml of the sample. It is the normal capacity of a burette, and that burette is filled with the titrant, and you first pipetted out the analyte into the conical flask, and pipette is a glassware which is used to measure exact volume of a particular substance. So in general, a pipette can measure 20 ml. So by taking 20 ml or any other fixed quantity of the analyte and placed it in the conical flask, then the burette should be loaded with the titrant solution. Titrant solution is a solution with exactly known concentration, and now you are doing the reaction between this analyte and the titrant, and the reaction should be continued till the reaction between them is complete. Now, the end point or the point at which the reaction is complete is known as the end point, and this end point is detected using an indicator. Suppose you are taking an analyte in the conical flask and you are adding the secondary agent called the titrant, and you have to add the titrant till the end of the reaction. That end is indicated by a point called end point. End point can be determined with the help of some reagents. They are called indicators. We can enter into more details of the indicators in coming slides and modules. The reaction is based on a balanced chemical equation, and the concentration of the unknown solution is calculated using the titration formula. The titration formula is nothing but N1 V1 equal to N2 V2. That is, number of milli-equivalents of the first component should be same as number of milli-equivalents of the second component. Now, another part of the present module is standard solution. It is very well clear that in volumetric analysis, there must be two types of solutions. One solution is the titrant, that is a solution with exactly known concentration. And the next one is analyte, whose concentration has to be evaluated. So, in volumetric analysis, we must have a solution with exactly known concentration. That solution A solution whose concentration is exactly known is called the standard solution. And now we are entering into more details of the standard solution. A standard solution, by definition, is a solution of accurately known concentration which is used in titrations. So, a standard solution must have exactly known concentration. The concentration of the solution is expressed in terms of molarity, that is in units of mole per liter, or normality, that is in units of equivalent per liter. In volumetric analysis, in many cases, for convenience, we are expressing the concentration in terms of normality. This is because the underlying principle behind the volumetric analysis is that number of milli-equivalents of the first component should be same as number of milli-equivalents of the second component. Number of milli-equivalents can be calculated from normality. Therefore, in volumetric procedures, we are generally expressing the concentration in terms of normality, that is equivalent per liter. We are considering the preparation of a standard solution. In order to prepare a standard solution, we have to proceed systematically like this. A specific mass of a substance, that substance is called the primary standard, is weighed accurately using an analytical balance. So, here you have to note one important point. You are hearing the term primary standard for the first time. We can study more detail in coming slides. But here itself you are hearing the primary standard for the first time. What is a primary standard? You know, a standard solution is a solution with exactly known concentration. A standard solution is prepared from a substance. That is called primary standard. So, to prepare a standard solution, first of all, you have to take specific weight or mass of a substance of primary standard. So, take some fixed quantity of the primary standard, weighed it accurately, and then made it into the solution. And this weighing up is with the help of an analytical balance. The substance weighed or the primary standard accurately weighed is dissolved in small quantity of distilled water. Now, the solution is transformed into a volumetric flask, a standard flask, and diluted with water up to the mark. That means, if you wish to prepare 250 ml of a substance, 250 ml of a solution, fixed quantity of the primary standard is weighed out, and it is dissolved in some amount of water. It is then transformed into 250 ml standard flask or volumetric flask. There is a marking, and you have to add extra water and make up to the mark. This is the procedure for the preparation of a standard solution. The solution, finally, you have to mix it very thoroughly. So, this thorough mixing enables uniform concentration. That is, the solution should be homogeneous. So, first of all, you have to take a fixed quantity weight of the primary standard, dissolve it in some quantity of water, and then transform it to the standard flask or conical flask, standard flask, or the volumetric flask, and then made up to the mark. Finally, you have to shake the solution. You have to mix the solution thoroughly to get a homogeneous solution. This is about the procedure for the preparation of a standard solution. Now we are discussing what are the important features of a standard solution. These are the important features of a standard solution. A standard solution must be pure, because by using that standard solution, by using the concentration and volume of the standard solution, we are evaluating the concentration of the analyte. Therefore, the standard solution must be as pure as possible, or it must be pure. And the second one is that it should be stable under storage. Suppose you prepared a standard solution and keep it for some days. You imagine the situation, let it undergo some dissociation. You cannot say that the solution is pure or it is just converted to some other components. That is, the standard solution must be pure and the standard solution must be stable under storage. The standard solution should be non-hygroscopic and non-volatile. What do you mean by the term hygroscopic? Certain materials will absorb moisture from the air and starts dissolving in that. The materials with such a property is known as hygroscopic materials, and here the standard solution should be non-hygroscopic and the standard solution should be non-volatile. That is, to any material extent, there should not happen any vaporization. The standard solution must react rapidly or immediately and completely during the titration or during its reaction with the analyte. Generally, high molar mass of the solute is preferred to minimize the weighing errors. That is, if you are preparing a standard solution and the standard solution is prepared by some materials with a high molar mass, that lead to minimization of the weighing errors. So, these are important features of a standard solution. Now, we are studying more about primary standard. I already mentioned about the concept of the primary standard. In volumetric analysis, you must have a standard solution. A standard solution is a solution with exactly known concentration. In order to prepare a standard solution, you have to take the weight of a substance. That substance is called primary standard. And these are the more details. A primary standard is a highly pure, stable compound that can be accurately weighed and used directly to the preparation of a standard solution. That is, with the help of primary standards, that primary standard can be easily converted directly to a standard solution. So, a material from which a standard solution can be prepared is called the primary standard. And a standard solution serves as a reference in volumetric analysis. So, a primary standard is required for the preparation of a standard solution in volumetric analysis. Based on the concentration of the standard solution, we are evaluating the concentration of the analyte. So, that material which is used in the preparation of the standard solution is called a primary standard. Now, what are the characteristic features or properties of a primary standard? These are the important characteristics of a primary standard. So, remember, a primary standard is a substance which can be directly weighed and converted into a standard solution. So, these are the peculiarities. The first peculiarity is that the primary standard must be pure or must be highly pure. The presence of the impurities may harm the quality of the volumetric analysis and the result may be erroneous. So, the second characteristics of a primary standard is here, it must be chemically stable and non-volatile. The primary standard must be stable under ordinary conditions and it should be non-volatile. The third condition is that does not absorb moisture. That is, it should not be hygroscopic or carbon dioxide from the air. That means the material under our consideration, that is, for a substance to be act as primary standard, it should not be hygroscopic, it should not absorb moisture from the air, it should not absorb carbon dioxide from the air. And high molecular weight of the material is preferred, and this is to reduce weighing errors. Now, the characteristics of primary standard continues. The primary standard should react completely and rapidly with the titrant. It should be non-toxic. That is, the primary standard should be non-toxic. That is, it should not have any toxic effect. And the last and the important characteristic feature of a primary standard is that it should be readily available and inexpensive. So, we have discussed some important points that are nothing but the characteristics of a primary standard. What is a primary standard? A primary standard is a substance that can be directly weighed and converted into a standard solution. Now, these are some examples for primary standard. Sodium carbonate, molecular formula Na2CO3. Its equivalent weight is 53. It is used as a primary standard, which is a base in acid-base titration. Another primary standard is oxalic acid dihydrate. Oxalic acid is COOH or simply H2C2O4. If it is associated with the two molecules of hydration, it can be called as oxalic acid dihydrate. Oxalic acid dihydrate is available in pure form. It is not hygroscopic. It is highly stable such that oxalic acid dihydrate can be considered as a primary standard. Definitely, it leads to the formation of an acidic solution, and the equivalent weight of oxalic acid dihydrate will be equal to 63. It is used as a primary standard acid in acid-base titration. Oxalic acid is an acid. If you are taking a fixed quantity of oxalic acid dihydrate and made up to the mark in a standard flask or volumetric flask, you will get a standard solution of oxalic acid. Definitely, oxalic acid is acidic, and the resultant solution is a standard solution which is acid in nature. Now, another primary standard under our consideration, which is highly useful in volumetric analysis, is potassium dichromate. Potassium dichromate is having the molecular formula K2Cr2O7. Potassium dichromate is available in the pure form. You can directly weight it and you can directly convert it into a standard solution. And the equivalent weight of potassium dichromate is equal to 49, and used as primary standard, potassium dichromate is an oxidizing agent. So, this potassium dichromate is used as a primary standard, that is oxidizing agent, which is useful in redox titrations. Redox titrations means a titration reaction between an oxidizing agent and a reducing agent. So, potassium dichromate can react with reducing agents like ferrous sulfate, more salt, etc. So, potassium dichromate is a primary standard which is used to prepare a standard solution, that is oxidizing agent. Now, more salt, its molecular formula is ferrous sulfate, that is FeSO4, ammonium sulfate NH4 twice SO4 with the 6 water molecules of hydration. So, the molecule ferrous sulfate ammonium sulfate 6H2 is called more salt. More salt is a good reducing agent. So, more salt is available in pure form. It can be prepared, it can be used to prepare a standard solution of more salt. So, more salt is definitely a primary standard. The equivalent weight of more salt is 392.13, and it is used as primary standard reducing agent in redox titrations. Now, a very important part of this discussion, it is nothing but calculation of weight in volumetric analysis or weight calculation in volumetric analysis. It is possible to calculate the weight of primary standard required to prepare standard solution using a particular molecular formula, and the weight required will be equal to volume into equivalent weight into normality divided by 1000. Suppose you wish to prepare VML of n normal solution with a solute having equivalent weight capital E. The weight required will be VEN divided by 1000. So, this is the expression for weight calculation that we use in volumetric analysis. Now, in this expression, V is the volume of the solution in ml, N represents normality, and E represents EQ or equivalent mass of the solute. Now, we are having some examples that demonstrate the weight calculation, the amount of the substance required to prepare certain concentration of a solution. Weight calculation, here we are discussing. This is the first question. How many grams of Na2CO3 with equivalent weight 53 are required to prepare 100 ml of 0.5 normal solution? You know that the expression for finding out the mass required is equal to Vn divided by 1000. In the present problem, equivalent weight E is equal to 53. Normality of the solution required is equal to 0.5. Volume of the solution should be 100 ml. So, volume 100 ml into equivalent weight 53 into normality 0.5, the whole divided by 1000, you will get to the answer. That is, weight required is equal to Vn divided by 1000, or substituting various values, you will get the normality, the amount of the substance required is equal to, weight required equal to 2.65 gram. There is another example. Find the weight of oxalic acid. Equivalent weight is given as 63. Required to prepare 0.1 normal, 250 ml solution. This is again a direct problem. The weight required is equal to VEN divided by 1000. In the present problem, volume V is equal to 250 ml, equivalent weight E is equal to 63, and the normality of the solution is equal to 0.1. So you have to multiply VE with N and divide the entire result with 1000, such that weight required will be equal to VEN divided by 1000, volume 250, equivalent weight is 63, and normality of the resultant solution should be 0.1. So 250 into 63 into 0.1 divided by 1000, that is equal to 1.575. So you have to take 1.575 gram of oxalic acid and dissolved in water to make it up to 250 ml solution. Now we are discussing another aspect of the volumetric analysis, that is nothing but secondary standard. We just now studied a primary standard. A primary standard is a material which is weighed out and directly converted to a standard solution. For a material which is used to prepare a standard solution is called the primary standard. Now we are considering another type of material that used in volumetric analysis. It is nothing but the secondary standard. A secondary standard is a solution whose concentration is not known accurately but is determined by titration with a primary standard. Secondary standards are prepared from reagents that are not pure enough or stable enough to be used as primary standard. Primary standard must have certain conditions, must meet certain conditions like purity, stability, etc. But secondary standard are materials whose concentration is determined with the help of using primary standards. Examples of secondary standard are shown here. It may be sodium hydroxide, HCl, potassium permanganate, etc. And now a very important question in front of you. Why sodium hydroxide is not a primary standard? A primary standard must be available in pure form. It should not be hygroscopic. It should not dissolve in water by absorbing moisture from the air. The solution should be stable. There are several conditions that we have already discussed. And now the question is in front of you. Why sodium hydroxide is not a primary standard? This is your answer. Sodium hydroxide is hygroscopic. What do you mean by a hygroscopic material? A hygroscopic material is a substance that absorbs moisture from the air or atmosphere and try to dissolve in it. Sodium hydroxide is hygroscopic, that is absorb moisture from the air, and deliquescent nature also, that means it dissolves in the absorbed moisture. This making it difficult to weigh and store accurately, thus preventing the preparation of a solution with the precisely known concentration. That means if you are taking NaOH as a primary standard, you will not get exactly known concentration solution. So, sodium hydroxide, owing to its hygroscopic nature and deliquescent feature, we are not recommend it as a primary standard. Now, end point and equivalence point. These two terms are closely related but have firm difference between the terms, and these two terms are highly significant as far as the volumetric analysis is concerned. First of all, we are discussing equivalence point. The point at which the amount of titrant added is exactly stoichiometrically equivalent to the amount of analyte present. That is, number of milliequivalents of analyte should be same as number of milliequivalents of the titrant. So, the end point is the point at which the amount of the titrant added is exactly stoichiometrically equivalent to amount of the analyte. This equivalence point can be determined theoretically using the balanced chemical equation. So, equivalence point is a theoretical quantity. That means you can determine equivalence point theoretically. Now, no excess of either reactant remains. That means at the equivalent point, either the analyte or the titrant is present in excess. They are in exactly similar quantities to bring about the reaction. Now we are discussing about end point. The end point during titration where the indicator changes its color, signaling the reaction is complete. So at the end point of a reaction or a titration in volumetric analysis, if the indicator shows a color change, you can simply assess that the reaction is complete. Now, it is the practical detection of the end point of a titration which should ideally match the equivalence point. A slight error between the equivalence point and the end point leads to titration error. A difference between equivalence point and end point leads to titration error in volumetric analysis. Now, introduction to indicators. We just heard about the term indicators. Indicators are materials which are used to find out the end point of a reaction. End point is an indication of the equivalence point which is very close to the equivalence point. So, with the help of some color changing reagents known as indicators, it is possible to find out the end point of a reaction. Now, indicators are substances that change color at a specific pH or at the end point of a reaction. That means whenever we reach at end point of a reaction, the indicator starts to change its color. By noticing that color change, we can assess the exact value of the end point of a reaction. End point is not the same as equivalent points, but end point is close to equivalent point. These indicators help in visually identifying the completion of the reaction or completion of a titration. Now we are having a discussion on various types of indicators. There are acid-base indicators which change color at different pH values, and examples include methyl orange, phenolphthalein, etc. Methyl orange shows change or color change from red in acidic solution to yellow in basic solution. This is the two different colors of the methyl orange indicator in acidic as well as basic medium. Now, methyl orange can be used in acid-base reactions or acid-base titrations in volumetric analysis, preferably the titration between strong acid and a strong base, and the titration between a strong acid and a weak base. There are two kinds of acids called strong acid and weak acid. There are two kinds of bases called strong base and weak base. A strong material will undergo complete ionization, whereas a weak substance will undergo only partial ionization. So, a good example for a strong acid is HCl, weak acid is acetic acid. A good example for a strong base is NaOH and a weak base is ammonium hydroxide. So, there are four kinds of probable titrations: strong acid, strong base, strong acid, weak base, weak acid, weak base, weak acid, strong base. So, you can use different kind of indicators, but you should note on very important thing: there is no visible indicator for a weak acid, weak base titration. That point is also very relevant. We can study more thing about such titrations in the next module. Now, the second indicator is shown here. It is nothing but a phenolphthalein. Phenolphthalein is colorless in acidic medium. The left hand side represents the colorless nature of the phenolphthalein indicator. However, in the basic medium, it turns it to pink color. So, this is the color of phenolphthalein in acid medium, that is nothing but colorless, and in basic medium, which is pink in color. It can be used in strong acid against strong base titration and weak acid against strong base titration. Now, we are continuing the type of indicators. The second category of indicators is nothing but redox indicators. Redox indicators change their color due to change in oxidation state. There are so many examples for redox indicators. These redox indicators are used in redox titrations or oxidation reduction titrations, or the titration between an oxidizing agent and a reducing agent. These are some examples for the redox indicators like ferroin, diphenylamine, etc. Other category of indicators are complexometric indicators. Complexometric indicators are used to determine the end point of complexometric titration, where we are using a complexing agent like EDTA and a metal ion analyte solution. Now, these complexometric indicators include eryochrome black tea, murex-oxide, etc. as examples. And the last category of indicators are here. They are nothing but adsorption indicators. They are used in precipitation titration, where we made some precipitation reaction by adding some precipitating agents, and these adsorption indicators used in precipitation titration by adsorption on the precipitate. Example for adsorption indicators are here. They are nothing but fluorescein and eosin. Now we are having an outlook, an overview on different type of titrations. This is the last part of the present module, and these are different type of titrations. The first category is acid-base titration. The acid-base titration is based on the neutralization reaction between an acid and a base. Indicators like phenolphthalein and methyl orange are used for this purpose. Typical example is the titration between sodium hydroxide against HCl. The second category of the titration is redox titration. The redox titration is otherwise called oxidation reduction titration, and it is based on some oxidation reduction reactions. It involves electron transfer between the species involved in the reaction. Typical example is titration of potassium permanganate against ferrous ion like ferrous sulfate or more salt. Third category of titration is complexometric titration. It is based on the formation of a coordination complex between metal ions and certain ligands. Use indicators like eryochrome black tea, and a typical example is the titration between the complexing agent EDT, ethylene diamine tetraacetic acid, and calcium 2+ ions. And this about the last category of the titration, that is nothing but precipitation titration. This precipitation titration is based on the formation of a precipitate when we react two reagents together. Silver nitrate AgNO3 is commonly used in the precipitation titration. Typical example is the titration between silver nitrate against sodium chloride. That all about the present module. Have a nice learning experience. Thank you.